Do you feel the vibes?
So we're going to solve these couple of word problems today, but then at towards the end of the chapter, I also have like a whole unit of just word problems. Okay. All right. So the width in millimeters of an animal's pupil, right? That's the part that dilates and stuff, is given by this. So d of x, that's the width, right? So where x is the illuminance of light shining in the pupils measured in LUX, right? So again, things that you've never really had to deal with, but here we go. Now we have to work with it and sift through this. So x is illuminance and it's measured in LUX. Whenever you come across a word problem, you want to identify what the variables stand for and what the unit of measure is, right? Because all of those are going to help you. So now it says to write a limit to describe the width of the animal's pupils when the light is at its minimum illuminance. Then find the limit and interpret your results. So when the light is at its minimum illuminance means what variable stood for that? X. So we want x to be at its minimum, so x approaching 0, right? So we want to find the limit of this function as x approaches 0. That's what we need, okay? So what we need to find is the limit of d of x as x approaches 0. So this is the limit as x approaches 0 of this function. Copy that down. Okay, now, yes, in the future, when you have functions like this, it'll be more complicated things you have to do to it. So you would have to you'd be allowed to use your calculator, you would graph it and so on. Now that's a different skill set. What I want to do right now is I want to focus on our number sense and how to make sense of these non-traditional looking numbers, right? Because we don't really deal with x to the power of negative 0.45. Okay, so let's see what exactly this is. And we want to be able to find a limit. What was I going to say? Mentally, right? Okay, so let's see what we're going to do. I'm going to explore this function a little bit. So this is the limit as x approaches 0 of, okay, so that negative exponent, I'm going to write it like this. So 152 over x to the 0.45 plus 85, and then 4 over x to the 0.45 plus 10. Okay, now, I don't like the way that looks. So why don't we multiply top and bottom by x to the 0.45. So this is the limit as x approaches 0 of 152 plus 85 x to the 0.45, 4 plus 10x 0.45, right? So, okay, now let's plug in x equals 0 to find the limit. When you plug in x equals 0, this is clearly 0 now, okay? This is clearly 0 now. So I have 152 plus 0, 4 plus 0. So this is just 152 over 4, 38. Okay, fine. So now we found this random number 38. Great. Good for you. Now this is the important part. Interpret your results, right? So what is it that this means? So this problem is talking about the width of an animal's pupil. So you know how like when you're in the dark versus when you're in like bright light, your pupils will either like dilate or they'll contract, right? Because if you have too much light, they'll contract so that there's not too much light coming in. And if you're in the dark, they'll dilate to take in the maximum amount of light so you're able to see, okay? So this is saying, so when the light is at its minimum illuminance, so basically when you have a minimum amount of light, right, entering the pupils, the width of the pupil is approaching 38, right? So it's like dilating in order for it to approach. Yeah. So the width in millimeters, it says. Okay. So when the light is at its minimum, the pupils approach a width of 38 millimeters. Okay? So what's important here is you've gotten the quantities laid out, right? The amount of light, the width of the pupil, you have proper units, and this is a limit. So it doesn't equal 38, it's approaching 38. That's important, okay? It may be exactly 38, or it may be 37.9, or it could be 38.1. We don't know. So that's important. You could also say like it, it like grows to 38 or it decreases to 38. That's up to you. Yeah. Because then you would be dividing by 0, right? Because this is 152 over 0. Well, again, this is the same as 152 over 0, right? But if you plugged in 0 here, what would you get? This wouldn't be 0. This would be 152 over 0, which means it's like close to infinity, plus 85, right? Because 0 is in the denominator, so you can't really plug in 0 unless you figure something out to make it defined. Okay, so that's why we did the little bit of algebra there. Okay, next, write a limit to describe the width of the animal's pupils when the light is at its maximum. So now we want, x approaching infinity. Then find the limit and interpret your results. Okay, so now we want the limit as x approaches infinity of d of x. So that's the limit as x approaches infinity. Okay, now that I've simplified my function, I'm just going to use that. Okay, the final product that I got, 152 plus 85, x to the 0.45, and then 4 plus 10, x to the 0.45. So here we're going to take, basically, like if it's a limit approaching infinity, we're going to take this over this, right? And then the 85 and the 10, basically 85 over 10 is what? 8.5. Okay? So here, yeah. From here, you can, but since I simplified it, I was like, you can use either step. So because you remember when the top and the bottom have the same degree, it's just the ratio of their coefficients. So now 85 over 10, how much is that? So that's 8.5. So yeah. So as the light approaches maximum illuminescence, okay, the pupils what is it? They can, or like approach a width of 8.5 millimeters. Okay. So in molecular theory, the root mean square speed measures the average speed of particles in a gas, defined by this formula, where R is the gas constant, T is the temperature, and M is the molar mass of the gas in kilograms per mole. Well, it's okay, right? It's okay because, right, you have to deal with things the way they come. Huh? Well, it should be because of R. Yeah, right. Okay, so find the limit as m approaches 0 of v. So this is the limit as m approaches 0 of the square root of 3RT over m. Okay, so m is in the denominator. As the denominator approaches 0, what happens to the entire fraction? It becomes infinitely large, right? So this is going to be infinity. So the limit is infinity, okay? Huh? Wait. Huh? Because as the denominator gets infinitely small, as the denominator approaches 0, the whole fraction goes up to infinity. It never is 0, right? Remember, the limit is never 0. Okay, so now interpret your answer. So what is happening here? So m is the mass, right? So as the mass of the particle approaches 0, so as the mass of the particle becomes infinitely small, the velocity will become infinitely large. Now, if you've taken chemistry, this will make sense to you. If you haven't taken chemistry, it's okay. You have to use the map to interpret the situation, right? So as the mass of the particle approaches 0, the average speed becomes infinitely large. Okay? Did you have a question? Yeah. No. It's okay. Remember what we said? So I said it becomes infinitely large. I didn't say it reaches infinity, right? So remember what we said? Infinity can take on different contexts within like the realm of the problem. Again, like if you're talking about a speed, if you're talking about a speed of like a runner, and you say, it grows infinitely. Okay, the runner's not going at like the speed of light, but in the context of his life, right? Okay, so find the limit as m approaches infinity. So now the limit as m approaches infinity of the square root of 3RT over m. Now as the denominator gets infinitely large, what happens to the whole thing? 0. And of course that makes sense, because if the particles get large, they're just going to get slower and slower and slower, right? So you guys come up with a sentence for that, yes? Okay. So okay, remember in chapter 10 when we did sequences and series? Yes? That was the best chapter. They're all the best chapters. I like all my children. So, remember how we had A sub n, right? An explicit formula for the terms of a sequence. And remember what I made you guys do in section 1 is I made you graph a couple of points to see if the sequence would converge or if it diverges. Remember that? And we said if if the values approached a certain point, then it converged. But we said if the points, didn't approach a finite quantity, then it diverges. Yes? Okay. We can do the same thing. This is a numerical approach. We can do the same thing algebraically using limits, because at the end of the day, what we're doing is when you're at like a sub 10 or a sub 100 or a sub a million at infinity, right? Where are the values approaching? So we can do that using limits, okay? So I had said initially to write the first 5 terms of the sequence. I'm not going to make you do that. I know you know how to do that. But let's find the limit. Let's see if it converges or if it diverges using limits, right? So the limit as n approaches infinity of a sub n. This is the limit as n approaches infinity of 4 over n squared plus 1. As n approaches infinity, now let's think about this for a minute. If n is infinitely large, n squared is even larger, and then n squared plus 1 is even larger. So now we have a very large denominator. What happens to the entire fraction? 0. So this becomes 0. That means it converges. It converges because the limit exists. So if the limit exists, if you have a finite value for the limit, then it converges. If the limit does not exist, if it goes to the infinities, then it diverges. So let's take a look at this one. Let's take a look at, the limit as n approaches infinity of b of n. So when you have an infinite limit, remember you take the higher degree over the higher degree. So what's the degree in the numerator here? I got n, 2n, so that's basically like 18n cubed. Because you've got the factors too. You have a 9 here, you have a 2 here, you're going to multiply all of them together. You have to look at the coefficients because if the degrees are equal to each other, then you have to compare the ratios of the coefficients. So you have to take the coefficients. At the bottom, you have 6n cubed. So that, I just lost -1 on a test. Because what did I forget? I didn't put the limit. So this should be the limit. As n approaches infinity, 18n cubed over 6n cubed. So that's just 3, so this too converges. But had we gotten, let's say, 18n to the 4 over 6n cubed, then it would have, the limit would have been infinity, right? And then, so this is how you write it. If it's like the limit as n approaches infinity, let's say b of n, and you say the limit is infinity or dne, and then you say it diverges. Okay?
Press start.